Hey everybody, tonight we have a polynomial, a third degree polynomial with a root that actually appears as a coefficient. Its negative square appears as a coefficient in the polynomial itself. So by root, sometimes called a zero, we mean that p at alpha is equal to 0. Okay. Again, you see this called a zero a lot of times in the modern algebra books. All right, so that's given, and again, the thing that makes this thing fly is that the root itself squared is the coefficient of x. Let's move along. And again, I'm just following my nose right here. P at alpha gives us this expression. We're taking alpha and just substituting it everywhere we see an x. Now notice right here we catch a break. We get alpha squared times alpha, and that's just alpha cubed. Okay, so you can see that the alpha cubed here cancels with the alpha cubed here. And since p at alpha is a 0, that implies that alpha squared is equal to the square root of 1295 when we take it to the other side of the equation. Okay. Now, if we take plus and minus square roots, we find out that we have the fourth root of 1295 as a 0, the plus and minus values. Okay, so not only is alpha a 0, but its opposite or negative is a 0 or a polynomial. It is a 0 of the polynomial. All right. Now, the fact that we have these two zeros induces a couple of linear factors here. Okay. And this is in the form difference of two squares. So when you multiply this out, you get this quadratic factor. Okay. Again, the fourth root of something times the fourth root of something is the square root of that something, right? So we know that p of x has this as a quadratic factor. And so since p of x is a third degree polynomial, we would anticipate one more 0 possibly. So I think we're stuck doing a long division here. So I'm going to bring this polynomial down and replace alpha squared with what it's equal to, and then see if we can do the long division. Okay. So what's going to happen right here? We'll have x squared minus the square root of 1295 is our divisor. Okay. And then we want to divide that into remember our original polynomial is this guy up here. And so we got x cubed plus x squared, and then we need to write all that down. So let's do that. We have x cubed plus x squared. Again, y'all, I'm just writing down our original polynomial with alpha squared replaced with square root of 1295. So we have, let's see here, minus square root of 1295x as the coefficient of x. Then also just as it appears as a constant term also, minus the square root of 1295. Okay, so we have minus the square root of 1295 right here. So the long division is going to require an x appear right here as the first term in our quotient. So x times x squared gives you the x cubed that you want to get rid of the x cubed. Okay. Now we'll take this x times minus the square root of 1295 and line it up right here. Okay, y'all, and then I always call this just a columnar subtraction. And so when you subtract, these two terms vanish right here. And so we bring down x squared minus the square root of 1295. But guess what? Okay, this is formally working out very easy. That's exactly what our divisor is, right? Okay. So that means we need to pop a 1 right here, and we're going to have x plus 1 as our quotient. And notice right here, you're just going to recopy this and subtract and get a remainder of 0, which would indicate that x plus 1 is also a factor of the original polynomial. Okay, and again, when you subtract right here, you get 0. Now, what does that mean? Do we have room on the next line here? That means that p of x, let me see here, do we got enough room? Yeah, I got it going on here. So that means that p of x is equal to this quadratic that we calculated right up here, okay, x squared minus like that times x plus 1. All right. Now that it's factored, it's easy to see what the zeros are. Or the I keep calling them the zeros because that's what I'm used to calling them. But that would mean that the zeros are equal to, and we've already calculated this. You're going to take the square root of this, and you get the 4th root plus or minus square root to this. So the zeros would be, and I'll just write it in set notation. You'll get the 4th root of 1295. Is one of your zeros. You will get minus the 4th root of 1295 as a 0, as a root. And also you'll get something that's much easier to write down, namely a -1. Now, y'all, it's a homemade problem that actually came from the Harvard MIT competition, where I modified it just slightly, but it's more or less the same idea as problem 1, year 2020. Now notice the reason why I chose this constant right here is 1295. You can say, if you really want to know, this is approximately 6, right? And this is approximately -6. And I did that just to make easy calculations. If you want to know those numbers, 6 to the 4th power is 1296, right? So these numbers are just a little bit shy of 6 and -6. 6 to the 4th power is 1296. It's not too hard to calculate. 6 times 6 is 36. 6 times 36 is 216. 6 times 216 is 1200 plus 96 is 1296. Okay, so this is just one less. So this would be a little bit less than 6 right here. Okay, and this would be a little bit less than -6. But anyway, in any event, y'all, these are the solutions. I thought it was pretty cool because you might anticipate having to use Vieta's formulas or something like that, but the presence of a 0 as a coefficient right here is really what made the problem relatively easy. But if you're not careful, you might not think about doing this step, and you might just try to do Vieta's, and I did it that way once, but there's absolutely no need to use Vieta's here. Just knowing that alpha is a root and that alpha is expressible as a root sort of the linear term leads to a relatively straightforward process without actually having to appeal to Vieta's result. But again, this circled area down here is the circled object is your solution set. Thank you for viewing.